morning, students. In the previous classes, we discussed about electric field, dipole, electric field due to the dipole and potential to the dipole. And what will happen when the dipole is placed in uniform electric field, like what is the car characteristics and how to calculate potential energy of the dipole. And we discussed all these concepts there. Now, today we will discuss first of all what will happen when the dipole is placed in non-uniform electric field and how to calculate the force acting on the dipole when it is placed in non-uniform electric field. So, first let us consider a dipole is placed in non-uniform electric field. It is force acting on a dipole placed in non-uniform electric field. That means force acting. We discussed already what is a uniform electric field and what is non-uniform electric field. So non-uniform electric field in the sense the field varies either in magnitude or in direction, or it may change both magnitude and direction from point to point. If it is remains same, both magnitude and direction of the electric field remains same both in magnitude and direction, then we call it as a uniform electric field. So now this is non-uniform electric field. So for example, I am taking this dipole is placed in a non-uniform electric field like this. This is a non-uniform electric field here, so the direction is different in different directions. Now suppose if a dipole is placed along this direction here. This is the dipole I am taking here. And so let us take the charges separately here. Like suppose this is say one charge Q plus Q and this is minus Q charge here. And I am taking here electric field is suppose say if I consider it as E, then here the force field will be E plus dE you may consider here, or E plus delta E you may consider here. That means I am taking that field is changing when you are traveling from negative from the position of the negative charge to positive charge, and so that it is a non-uniform electric field. Here the field is we are taking it as E, and here the field is E plus delta E you can write here. And so now we know the force acting on the positive charge, net force acting on the dipole, now we can write as so force on positive charge minus force on the negative charge, because their directions are opposite each other. And so now here we can write this as force acting on the positive charge is nothing but E plus delta E into Q minus, and this value will be A into Q. The force acting on this negative charge, that will be along this direction, force acting on the negative charge, and the force acting on the positive charge will be in the direction of this field. And so now here so therefore I can write this as Q into delta E we can write, right? So now here I am expressing this value. Suppose here I am taking this some L as the length of this dipole here. For example, here I am taking L as the length of the dipole, and therefore I can write this as Q into this delta E by delta X into A. So that we are expressing like this. We are multiplying with some length and dividing with some length here. And now this Q into L will become the P, because here itself we are taking L itself as a length of this dipole here, and so then Q into L itself is the dipole moment here, and so I can write this as P into delta E by delta X. Actually this is nothing but we call field gradient. So in general we can express it as so we express that force as P into dou E by dou R or dou X we can write here, or let us write in terms of as a function of this X here. So I am writing in terms of gradient dE by dR. So with when a field is varying with the R, then force can be expressed like that. And actually you can also write it instead of this you can also write it another way. That means so another way of expressing this we can write as, we know already this potential energy we can write as right? And now here that theta will be, in this case we are assuming that when the dipole is placed in a particular region, in that small region, the field and dipole moment both are in the same direction we are taking, and so I can write this one as minus P cos theta value is 1, since that theta value is equal to 0. And therefore we know this another relation as F is equal to minus du by dr. Substitute that value here, so this implies you can write this F is equal to minus d by dr of P, we can write. So therefore this F is equal to minus P, then minus over minus plus you will get here, so then it is P into d by dr, you can write. So that will be the expression for this force acting on the dipole. So in terms of potential energy we can write, or in general way of in general also we can derive like this. So now from now onwards, whenever a dipole is placed in the non-uniform electric field, so the force acting on the dipole is given by like this, E P into d by dr. And so actually when it is placed in the uniform field itself, there we discussed that how the force and torque acts on the dipole when it is placed in uniform electric field and when it is placed in non-uniform electric field. So whenever the dipole is placed in non-uniform uniform electric field, remember these points. Net force acting on the dipole is always 0 whenever a dipole is placed in uniform electric field. But torque acting on the dipole may be 0, may be non-zero. That depends on its orientation. We derived the formula also in the previous class, like tau is equal to P sin theta, right? And so that that is the case when it is placed in uniform electric field. When it is placed in non-uniform electric field, the torque acting on the dipole may or may not be 0, and force also may or may not be 0. That means we can't conclude that force acting on the dipole is non-zero when it is placed in non-uniform electric field. It may be 0 even though it is placed in non-uniform electric field. So we will discuss some problems now. If the force acting on the dipole may be 0 even when it is placed in non-uniform electric field. That means it depends on actually how the dipole is placed in the electric field, the orientation of the dipole, how it is placed in the electric field, non-uniform electric field. So if any force is acting, then that force in non-uniform electric field can be calculated by using this expression, right? So that you need to remember, P is the dipole moment of this given dipole, and d by dr is the variation of this electric field along the direction of this dipole here. So now let us see some problems based on this. So you have to remember those points. What is the force acting on the dipole when it is placed in uniform and when it is placed in non-uniform electric field? I think we mentioned already in the previous discussion when you are calculating the torque. So here also, if you want, you can write once again. Write it as a note, the points. When the dipole is placed in uniform electric field, when the dipole is placed in uniform electric field, net force acting on the dipole must be 0, but torque acting on the dipole may be 0 or may not be 0. Next point, that is about uniform field. Next point, when the dipole is placed in non-uniform electric field, both net force and a net torque acting on the dipole, may or may not be 0. And here we can add one more point, that is regarding the non-uniform field produced by a point charge. So here suppose this Q is a point charge here, then a dipole is placed here. You may consider now in any direction. Now we are placing a small dipole in the field created by this point charge here. Now suppose I am taking this dipole is placed like this. Suppose say this is the negative charge and this is the positive charge here. A small dipole is placed there along the direction of the field here. Here we know the field direction will be along this direction. And so now force acting on the this positive charge we can write as like E1 into Q. And here the force will be E2 into Q. And we know this electric field will be a point charge, will depend on the distance. E is inversely proportional to R square. And so at this point, field will be greater in magnitude when compared to this, right? And so that here net force acting on the dipole is not zero in this orientation. Now suppose if I am considering like this. If you consider that like dipole is placed here, let us take this as positive charge and this as a negative charge here. Now this is a point charge. Now again electric field due to this charge will be along this direction at this point, and electric field here also along this direction here. And so therefore here the force is say along this direction, but here the force is attractive force like this, since it is a negative charge. Now the forces are equal in magnitude. Here and here electric field magnitude will be same, because this distance and this distance will be same here, right? So electric field is equal in magnitude, but the force directions are not same. So if you resolve them into components, then you will get the conclusion here. The net force acting on the dipole will be there along this direction, because these two components will cancel with each other. Here if we resolve this F into component, so here you will get like F cos theta along this direction, if this angle is theta, and this will be F sin theta. And similarly for this F, if we resolve this into components, this angle will be theta we are taking. So this is F cos theta, this is F sin theta you will get. So these F cos theta components will cancel with each other, and these two F sin theta, here F sin theta components will be added together, and so that the net force acting on the dipole will be along this direction. And so that means if the dipole is placed in non-uniform electric field produced by a point charge, then you can conclude that net force acting on the dipole is non-zero, is always non-zero in the uniform field produced by a point charge. But the torque may or may not be zero. You can see in both the examples. In this example, torque is zero because these two forces are acting away from each other. But here, if you are taking here also the torque acting on this will be zero. If you are changing the orientation, torque may not be zero here. So that depends on this. And here actually these two, the torque due to these two forces, these two components will be zero. These two components will produce a like a clockwise torque here about the center of the dipole. And so that means now torque may or may not be zero, that depends on the orientation of the dipole. But here the dipole is placed in non-uniform field produced by a point charge, then net force acting on the dipole is non-zero. So write that as the next point in that note. So write that when the dipole is placed in non-uniform electric field, when the dipole is placed in non-uniform electric field produced by a point charge, then net force acting on the dipole, is non-zero. But torque acting on the dipole may be zero or may be non-zero. Let us find some problems based on this force calculation. Let us take this as an infinite line of charge sheet. This tends to infinity, having this charge density lambda. Now we are placing the dipole here. So now different orientations are there here. A small dipole is placed like this. small dipole of length 12, dipole moment P is placed at a distance of r from this. So write it as a problem. A small dipole of length 12, small dipole of length 12, in brackets in the right this L is very much small dipole of length 12 is placed nearby a infinite line of charge having linear charge density lambda at a distance r in brackets now write this r is very much greater than this of L at a distance r as shown in the following cases. Now find the force acting on the dipole. In each case. This is the dipole moment direction here. This is our case 2. Case 1 is like this. The dipole is placed parallel to this infinite line. And case 2 is placed like this, perpendicular. But in both the cases, the dipole and the line of charge are lying in the same plane. Now in the third case, I am taking like this. Suppose this is the infinite line here. Then actually the dipole will be like this. The dipole is like this in the sense it is perpendicular in plane. That means now here the dipole is like this. If the line of charge is like this, then the dipole is placed like this. If suppose say that this dipole is placed along this y-axis, line of charge is placed along the y-axis, then it is placed along this z-axis like this. Both are perpendicular to each other. So that way I will discuss it later. So these are the three cases here. This is a case 3. So in these two cases, both the dipole and line of charge are in the same plane. So now let us consider how this force acting on the dipole in each of these cases here. Suppose I am taking this first case now. So as the dipole direction is given like this, I am assuming suppose say some negative charge is present here and some positive charge is present here, right? And so now clearly in this case we can observe that this is an infinite line of charge, the field at the location of this minus q and the plus q are same in magnitude. Because we know the electric field due to this line of charges lambda by 2 pi epsilon naught r at a distance r if we consider, right? That is the electric field produced by infinite line of charge. Now here you can observe that the distance of this minus q from this line of charge is r and the distance of this plus q from the line of charge is also r. And so that the electric field strength acting at the positive and negative charges will be same. So here also that E will be there along this direction and here also same E will be there along this direction here. And so now here the force acting on the dipole will be like this, F1, and force acting on the dipole, this charge will be F2 like this, negative charge. And therefore the net force in this case is, suppose I am writing F1 minus F2 I am writing here. So which is E into Q minus E into Q. Therefore you can write this that E value is same, which is given by this expression here. So that net force acting on the dipole is 0 in this case. Is it clear? when the dipole is placed parallel to this line of charge such that they are lying in the same plane, the distance of positive charge and the distance of negative charge from this line of charge will be same. And so automatically the electric field will be same. And now the force will be equal and opposite. And so they cancel with each other. So that net field, the net force acting on the dipole is zero. So that is the point which we mentioned previously as a note. When the dipole is placed in non-uniform electric field, now it is a non-uniform electric field only. Because due to this line of charge, the electric field will be different at different points and it is different at different distances. So it is inversely proportional to R here. And so now the field is a non-uniform field. So when the dipole is placed in non-uniform field, here the force acting on the dipole is zero. So we mentioned it may be zero, may not be zero. Here this is the example for where the dipole experiences zero force in non-uniform electric field. Right? Now let us come to this second example, second case here. Now the dipole is placed perpendicular to this line of charge. So when it is placed perpendicular to this line of charge here, now we can simply observe that the field is varying when you are moving from this say negative charge to positive charge. Because as we discussed previously, the distance of the negative charge and the distance of positive charge is different here. And so definitely some field is varying. And so we can calculate that force by using our previous formula. And so that I am writing here for case 2, the calculation of this force. And so now here the E value we can write as electric field at a distance we can write as lambda by 2 pi epsilon naught r. And force acting on the dipole is, so force acting on dipole we can express it as F is equal to P into dE by dr we can write, right? And so this is nothing but F is equal to P into d by dE, dr of E value substituting here lambda by 2 pi epsilon naught r. And therefore this can be expressed as this is minus P lambda by 2 pi epsilon naught into r square. That means 1 by r differentiation, that is minus 1 by r square you will get. So this force that indicates that the negative side indicates that the force between them will be an attractive force. Because here negative charge is closer to the line of charge and so net force will be along this direction here. So that is the conclusion what we are getting here. And so the magnitude of force if I write here P lambda by 2 pi epsilon naught r square. So if the dipole is placed like this, then the force will be attractive force. If we reverse the dipole direction, then the force will be repulsive force will get. Here in terms of potential energy, right here we need to write actually P into dE by dr into cos theta we need to write. If we derive it from the potential energy as we discussed previously, we will get that. Potential energy is minus P cos theta and F is equal to minus du by dr. So if we substitute here P cos theta you will get. So now in that formula, for example, if you consider this, now the field and dipole are in the same direction, so cos 0 you will get. So that here you will get the negative sign here. And if it is cos 180, then you will get this positive sign there. That means if the dipole is reversed like this, then cos 180 you will get, which indicates the repulsive force. So whether the force is attractive or repulsive, simply you can identify whether negative charge is closer to the line of charge or positive charge is closer to the line of charge, right? If the negative charge is closer, then automatically the force between them will be an attractive force. If positive charge is closer, then automatically the force between them will be repulsive force. That we can decide the magnitude of whether it is attractive or repulsive. So this is the magnitude of this force now. So that is the second case. Now we can observe that it is a non-zero force. So non-zero force is acting on this dipole and it is placed in non-uniform electric field. Now let us come to the third case here. So first of all you should understand how this dipole is placed in it. So again I am saying that when this line of charge is placed like this, now the dipole is placed here. Line of charge is vertical. Now the dipole is placed perpendicular to this like this. Now this is the second case also perpendicular only, but that perpendicular will be like this. Both are lying in the same plane. Now here both are lying in the perpendicular planes here. This is along this direction and now the dipole is placed like this. That is the third case. Now let us see how to calculate this force in the third case. So here when you are considering like and taking this line of charges like this, it is perpendicular to this is the line of charge and the dipole is supposed to be placed like this. I am mentioning this dipole is placed here. This is supposed to be plus q, this is minus q. And this distance is r at a tensor, so that this will be L and this is A, right? That means I am taking this line of charges like this. I am taking line of charges perpendicular to this plane and the dipole is placed like this. That is the situation what we are considering here. And so now here I can write the electric field due to this line of charge at this point will be along this direction. And so force is also in the same direction. That force we can write as eq. Now the field due to this will be along this direction, and so that force will be along this direction. Force acting on the negative charge is opposite to this, so which is again eq. And by the symmetry you can say that this distance is nothing but say under root of r square plus l square, right? And so these two distances are same, and so this magnitude of electric field at this point and magnitude of electric field at that point both are equal. And so now suppose I am taking like this angle is theta I am taking here, so that this angle will be theta. So you can take this angle as theta here, right? Now let us resolve these forces into components here. So here we need to consider like this angle is theta here. So I am writing this eq value here. So this angle is theta. Now I can write this component as f cos theta. And along this will be f sin theta. And similarly here this component is f cos theta like this, and this component will be f sin theta unit. So now clearly you can observe that this f cos theta and this f cos theta both are equal in magnitude and opposite in direction, so they cancel with each other. And only we need to add these two terms here, f sin theta plus f sin theta. So first I am writing this electric field here. So lambda by 2 pi epsilon naught into the distance of that point is under root of r square plus l square we need to write. And therefore this net force acting on the dipole we can mention it as 2f sin theta we can write. Let us substitute those values here. So it is nothing but 2 into f is eq into sin theta we need to write. Now let us substitute that e value and the sin theta value by using this diagram. And so 2 into e value is lambda into q by this is 2 pi epsilon naught into under root of r square plus l square, that is eq, into sin theta we can write by using this diagram, right? And so that is l by opposite side by hypotenuse, which is r square plus l square we can write here. Therefore, this we can express it as 2 into L into Q. That is nothing but our dipole moment, because here we are taking the dipole length as 2L here, right? And so I can write this as P into lambda by 2 pi epsilon naught into R square plus L square. Since we are using this Q into 2L as P. And here but L is very small when compared to R. Therefore, this net force can be approximately taken as P lambda by 2 pi epsilon naught R square we can write here. So, this is a force acting on this. That means I am taking this L square will be negligibly small when compared to that of R square. So, L square value I am neglecting here. Then this is the expression for force acting on the dipole here. When it is placed like this, perpendicular to the line of charge, in a perpendicular plane. So like that we can calculate the force acting on the dipole when it is placed in non-uniform electric field. So in the non-uniform electric field, force may be 0, force may not be equal to 0. That depends on that how the dipole is placed there. Next here, let us consider if the dipole is placed in uniform electric field, the time period of oscillation we need to calculate here. Time period of dipole in time period of dipole in electric field. external electric field is considered when it is based in external electric field. Now simply we know that simply what we are taking is, if suppose this is the electric field here. Now the dipole is placed like this, for example. So that this is negative charge and positive charge here. This is the direction of this electric field. We know already, we discussed already, some torque will act on this. So if the dipole is like this, then the torque is 0. Now it is displaced slightly to this position here, to the small angle theta, and then release it. If I release from this position, then what will happen? Because of this torque, automatically the dipole will comes back to its into the direction of this field here. Right? Now that torque is nothing but a restoring torque. Whenever you are displacing the dipole from the direction of the field like this, then automatically it will comes back to this direction here. And actually, when you release from that position, it will execute simple harmonic motion. It will oscillate like this. If the theta is small, then you can consider it as a simple harmonic motion here. So let us write this. That means we are assuming here like this. Consider a dipole of dipole moment P is placed in. Consider a dipole of dipole moment P is placed in uniform electric field. Uniform electric field of intensity E. Uniform electric field of intensity E. If the dipole is slightly displaced from the direction of the field and released, if the dipole is slightly displaced from the direction of field and released, then it executes simple harmonic motion. Then it executes SHM. And whose time period can be calculated as follows. Whose time period can be calculated as follows. So restoring torque. So I can write this as tau is equal to minus PE sin theta. This torque expression we already derived. Here we are naming it as restoring torque because it restores the position of the dipole here. Because of this torque only, the dipole will again comes back here. The dipole is released here, the torque acting on the dipole will be like this. So automatically it comes back here. And we know this torque we can write as I alpha. This is equal to minus P into sin theta. Therefore alpha is equal to minus P by I into sin theta we can write. So if theta is small, then sin theta can be replaced with theta. And therefore this alpha is equal to minus P by I into theta we can write here. So from this you can observe that this will be our condition for this SHM here. That means if angular acceleration is directly proportional to the negative angular displacement, then we can say that motion will be simple harmonic motion, which is similar to that of our A is proportional to minus x in SHM. And so now here this alpha is angular SHM, this will be. So alpha is equal to minus PE by I into theta. That means it is alpha is proportional to the minus theta we can write here. And so from this what we can conclude is the motion will be simple harmonic motion. And it will be simple harmonic motion only when theta is small. So if theta is not small, you can't replace the sin theta by with the sin theta with theta. So if sin theta, still if sin theta is there continuing in that expression, then you can't call it as a simple harmonic motion. It will be just a periodic motion, we can say that. Is it clear? So when the theta is small, then it executes the simple harmonic motion. So compare with alpha is equal to minus omega square theta. Therefore, omega is equal to under root of P by I will get. And from this time period T is equal to 2 pi by omega we can write here. And if we substitute there, then you will get this time period of oscillation of this dipole will be 2 pi under root of I by P. So this expression for time period of this dipole here. See once again in this 2 pi into I by P, where I is the moment of inertia of this dipole about its center of oscillation, and and P is the dipole moment of the dipole, and E is the intensity of electric field present in the region. So those are that is a simple expression for this. As we completed the SHM in the first year syllabus, so then this calculation will be very easy for you. Just we are writing this term, this expression just now we completed. So then just we are writing this term is equal to I alpha, that is equal to minus P sin theta, and then we are replacing this sin theta with the theta. So that this is our direct SHM equation. And from that you will get the omega value. From that you can write the time period calculation, right? So it is the time period of this dipole that is oscillating in a uniform electric field. Now let us see some problem based on this time period calculation. So these are two line of charges here having this charge density say lambda. This is say plus lambda, this is minus lambda, and its length of this rod is L. This length is L, and those are connected by a light rods in the sense massless rods. Now this total arrangement is suspended in an electric field, uniform electric field like this. This electric field is lying in the space itself. Now it is slightly displaced and then released here. Now it executes SHM. That the dipole. Now it will behave like a dipole. That because two rods are having opposite charges here. This is positively charged, and this is negatively charged here. So those two rods will form a dipole here, and so that dipole will execute. That means here this is one rod, for example, this another rod. This is lying in this plane. Now the electric field will be like this. And so now we are displacing it slightly from the direction of this electric field, then execute the simple harmonic motion here. So that we need to calculate here. That time period of oscillation we need to calculate. So write that problem. Two identical rods, each of mass M and length L, each of mass M and length L are having uniform charge density, plus lambda and minus lambda. That means on one rod it is plus lambda, other rod it is minus lambda. These two rods are connected by two light rods, of length d. This system is placed in uniform electric field. Such that it is free to rotate. About its symmetrical axis. If the system is displaced slightly from the direction of field and release, find its time period of oscillation. is time period of oscillation. So now this is our formula for this time period of oscillation here. That means 2 pi into under root of I by P into E we can write. So that is our formula. So just we need to apply this formula here directly. Means same derivation, when it is displaced slightly from the direction of field by theta, then torque acting on the dipole is P sin theta. The same calculation we need to write, so directly I am applying that formula. And so now here we need to write about this P first. So this P is nothing but actually we need to write Q into distance. So the distance between them is D we are taking here, distance between those two charges. Now Q is nothing but charge present on this, magnitude of charge present on this one of the rod. So I can write it as lambda into L. So lambda into L into D. So this is the field acting, dipole moment of this dipole here. And next we need to write this dipole moment of the system here. So dipole moment of the system I can write this as moment of inertia of the system we need to write. I is nothing but. So moment of inertia of the system about the symmetrical axis. Now the object is like this. For example, this is the direction of the field like this. Now we are displacing. That means suppose say this is the direction of the field. For example, if you are taking, then our dipole moment will be like this. This is suppose say positive, negative, positively charged, and this is a negatively charged. Then this will be equilibrium position. Now from this position we are displacing it slightly like this. We are displacing it slightly like this, and then we are releasing here. Then it executes simple harmonic motion like this. This plane will execute simple harmonic motion like this. And so that it is executing SHM about this point here. This is our axis of rotation here. So about the axis of rotation, we can write its moment of inertia here. That means about this axis we need to write here. About this axis, the system will execute the simple harmonic motion. So about that axis, write ml square by 12 plus md square by 4. This is ml square by 12 plus md square by 4. About this axis, this we can write this as into 2, right? Because such a 2 rods are there. That means our arrangement will be like this. Dipole when it is initially parallel to this. So this is our negative charge and this is a positive charge here. These two are connected here. Now this is the direction of this electric field. So initially the dipole moment is also the same direction here. Now what I am saying is from this we are displacing here. Now suppose it is displaced slightly to this position here. So that now the dipole moment will be like this, whereas electric field will be like this. Now this is our positive charge and this is a negative charge here. Right? So if you displace the rod from this, now I am saying it will rotate about this axis, right? This P will again comes back to this direction, and so it should rotate about this axis here. The system is rotating about that axis. So about that axis, now I am writing the moment of inertia of the system here. So that is for one rod I am writing like about this axis in the sense, about this axis and perpendicular to this plane in the sense. So I can write this as ml square by 12 plus md square by 4 we can write. So into 2. Because two such rods are there, so I can write this as ml square by 6 plus md square by 2 by multiplying with the 2. Therefore, this time period we can write as t is equal to 2 pi into this value is ml square by 6 plus md square by 2 by p into l into d. So p value is lambda into l into d into e. You can take LCM and you can simplify that. So m if I take common, then it will be L square plus 3d square by 6 lambda L into d into e. That will be the expression for this kind of oscillation of such a dipole. Next, let us see one more similar problem. This is a circular rod. placed in uniform electric field like this. And it is having this part is carrying some positive charge here, of positive charge density lambda, and then this part is carrying some negative charge here, minus lambda. Now it is placed in such a uniform electric field of intensity like this. Now it is slightly displaced when it is oscillating. Then we need to write time period of oscillation of such a system. Similar problem. But here first we need to write, we need to calculate this dipole moment here, because it is a continuous dipole now. Previous also continuous only, but we can write that easily because positive and negative charges are separated by a finite distance. So now here it is, write this problem. A circular arc of mass m and radius r. A circular arc of mass m and radius r, which is obtained a total angle of 2 theta at its center. Which is obtained a total angle of 2 theta at its center. Is placed in uniform electric field of intensity E. Uniform electric field of intensity E. Half of the arc is having linear charge density plus lambda. Half of the arc is having linear charge density plus lambda, and other half is having minus lambda. And other half is having linear charge density minus lambda. If it is slightly displaced and released, then find its time period of oscillation. So same problem, just we need to calculate this dipole moment here. So from the dipole moment I am taking the calculation like this. So here I am taking a small element here. This angle is for example phi, so that this is d phi. And such an identical element I am taking here. So this is plus dq you can consider, and then this will be minus dq, because this side negative charge is there here. This side positive charge is there here. So now for this small element we can write the dipole moment is, for small element dp is equal to, so dq into the distance between them we need to write here, this distance between them. So by using this triangle we can write that this is r sin phi and this is also r sin phi. So I can write this as 2r sin phi. Now the dq value we can write as q by, now this charge, this length of the arc we need to write. So that is r theta. This is the charge per unit length. This charge q is distributed in this length of it, right? So its length of this arc we can write as r theta. That is charge per unit length into length of this element we can write as r into d phi into 2r into sin phi. And so now we can write this as r we can cancel here. So finally I can write this as 2q r by theta into sin phi d phi. So this is our dp value. So for continuous charge distribution we solved already some problems. So to calculate the total dipole moment for the whole system, we need to verify whether the dipole moment due to all the elements is in same direction or in different direction. So where the dipole moment direction is nothing but from negative charge to positive charge. So along this direction here, right? So due to all such elements, the dp will be in the same direction, upwards only we get. And so you can integrate this expression directly. Write this as 2q r by theta into integral of sin phi d phi. And so now this phi value varies from 0 to theta, right? because from here to here we need to integrate. So here when it is here it is 0 and here it is means theta. And so therefore it is 2qr by theta into sin phi value will be minus cos phi and limits are from 0 to 5. Therefore this dipole moment I can write as 2qr. So this value is nothing but this lambda value is given here. So I think here you can substitute that lambda value. Finally I will substitute that. This value will be 1 minus cos phi, you can write. So therefore this p is equal to, now this q value is actually here it is given in terms of lambda only. So this value can be replaced with the lambda value. And so further you can write that value as 2r square into lambda into 1 minus cos theta, you can write here. So this is from 0 to theta limits. Right? Just this q value, this lambda value is nothing but q by r theta. So q is equal to r theta into lambda we are writing here. So if we substitute that value, theta will be cancelled here, all into r square will be r square into lambda. So it is our now dipole moment. So that dipole moment now we can directly use in our formula there. And therefore this time period calculation we can write as 2 pi into under root of I by p. So we will directly I value we can substitute here. This is nothing but I by mr square we can write here. Because it will rotate about this center only. When it is rotating about its center, we can write that the moment of inertia of the circular arc is same as that of our. That means we need to displace like this. Our dipole moment will be now in this situation. Our dipole moment will be parallel to this E1. So we need to displace the dipole like this. About this arc, we need to about this center only we need to displace like this. And so moment of inertia about the center, this point only we need to write here, center of this full circle. And so when it is center of the full circle, we can write its moment of inertia as mr square into this p value is 2r square lambda into 1 minus cos theta into E. So this value we need to write here. Therefore I can write this expression as 2 pi into that r square will be cancelled. So m by 2 lambda into 1 minus cos theta into E. So this is our expression for this time period in that case. So like that we can calculate the time period in any case. Whenever time period is given, then that means whenever such a dipole is placed in uniform electric field is given, so that is our time period calculations. That means we need to think about this p value calculation. So if p is given for you, then the problem will be easy. Directly you can substitute in that. Then moment of inertia we need to calculate. That we know already. We discussed in that moment of inertia calculations in that rotatory motion topic. Next, let us see this. When the dipoles are placed together, then they will interact with each other. Then interaction between the dipoles we need to write here. Before that, I will give one problem and solve yourself such a similar problem. This is sphere of radius r and having some charge q distributed on this uniformly. Now the dipole is placed here along this direction. A small dipole is placed like this. This is minus q and plus q. Or let it be dipole moment is p here at a distance of x from it. So dipole moment is p is given. Now the dipole is slightly displaced and then released. Time period of oscillation we need to write. These are the point charges. So point charges in the sense its mass is m and length of this dipoles is u. So that is our situation. Length of the total length will be 12. A dipole is placed at a distance of x from a uniformly charged sphere as shown in figure. The total information is there. The charging q radius it is placed at a distance of x. These are the 2 point charges of mass m and the total length of the dipole is 12. if the dipole is displaced slightly and released, if the dipole is displaced slightly and released, then find its time period of oscillation. Then find its time period of oscillation. And also find the amount of work done in rotating the dipole from given position to through an angle given position to through an angle 180 degrees. Through an angle 180 degrees. To solve that problem, same process. Just here we need to write the electric field at that point. So which we discussed already. Field to this solid sphere, kq by r square we need to write. It means here kq by x square. That just that field we need to substitute there. And then next let us write this force between two dipoles. So force between two dipoles. So force between two dipoles we can write it as, suppose say in these different cases will be there. I am taking that as case 1. So when the two dipoles are placed like this. This is suppose say P1 and this is the P2, such that their centers are separated by a distance. So that is our situation. That means two dipoles are placed along the same line. So that we are taking as case 1. When the two dipoles are placed along the same line, then we are calculating the force between them. So that is our first case. So mention that first case when the two dipoles are placed along the same line. So now in this case, generally to calculate the force between those two dipoles, we use our potential energy. So just we derived an expression for potential force acting on the dipole when it is placed in non-uniform electric field. So in that we use the potential energy formula to derive the force between them, force between the two charges, right? So now here also we use that same thing only. So now we are going to write the potential energy of the second. You can write the potential energy of one dipole due to the other. So here we are taking this potential energy of this dipole I am going to write here. So that means first I am writing the field due to this dipole at that point. Field due to P1 at P2. So this value we can write as, that means it is an axial line here. At an axial line we can write as 2k P1 by r cube. This is our electric field due to a dipole on its axial line formula. And so now this electric field on the dipole at that point, direction is also important for us. For an axial line we know already, for an axial line the direction of electric field is in the direction of this dipole moment. So here the dipole moment is along this direction, so it produces the field on the axial line also in the same direction. So that means here I can mention this E1 will be along this direction here at that point, right? And so now in this electric field, now this dipole is present. So whenever a dipole is placed in external electric field, we know it possesses some potential energy. So that potential energy formula is minus Pe cos theta, where theta is angle between P and E. So therefore I can write this as so potential energy of this dipole we can write as minus P2 into E1 into cos 0, because both are in same direction, minus Pe cos theta formula. Therefore I can write this value as minus E value I am substituting from this E1 value. So I can write this as 2k P1 P2 by r cube, right? Now we know the force and potential energy relation. We know F is equal to minus du by dr. So let us substitute that value now. So d by minus d by dr of minus 2k P1 P2 by r cube. So the constants you can write outside. So it is 2k p1 p2 by, means its differentiation is nothing but you will get like I'm writing here minus 3 by r power 4 you will get, and therefore it is f is equal to minus 6k p1 p2 by r power 4. So this is the force between those two dipoles. There the negative sign will indicate attractive force between the two dipoles there. So the dipoles will attract with each other. And so now here we can write this expression as so I am writing this modulus here 6k p1 p2 by r power 4. You may mention that this value attractive force. So this is a force between two dipoles when they are placed like this. That means how to say attractive force in the sense you can cancel the charges actually here. This is negative charge and this is a positive charge here. Or you can explain like this. So this is an electric field produced by this. So in this if I cancel the negative and positive charges like this. This is the negative charge and this is a positive charge for this dipole. Now the electric field at the negative charge is greater in magnitude, because when you are moving away from the dipole, this electric field goes on decreasing with r cube, inversely proportional to r cube here. So then negative charge is closer to this dipole here. So then here strong field will be there. So automatically here strong force will be there when compared to the positive charge, force on the positive charge. And so net force will be directly like this. So that is the significance of the negative sign here. It is an attractive force. The force between the two dipoles is attractive force. And so here you should also remember this force between two dipoles is inversely proportional to this r power 4 here. So that also should remember. Whereas between two point charges we mentioned that force is inversely proportional to r square, but here it is inversely proportional to r power 4. So this is the case 1. So let us see the second case. Same procedure when the dipoles are placed parallel to each other. Suppose this is P1 and P2. Now they are separated by distance r. So when the dipoles are placed like this, we need to calculate the force between them. Similar procedure. First we write the electric field produced by one dipole. Previously we discussed the electric field produced by P1 and P2. You may take the reverse also. The electric field produced by P2 and P1 you may write. You may write potential energy of this P1 you may write. You can do the reverse calculation also. Both will be same only. So one dipole is produced in the field we assume, and so other dipole is lying in the field produced by the first dipole we consider here. So here also I am taking the same process. So at this point I am taking the field. Field due to P1 at P2. So this field we can write as E1 is equal to. Now you can observe that this point is lying on the equatorial line of this dipole here. On the equatorial line, the direction of the electric field due to the dipole is, we discussed already, opposite the direction of the dipole moment. So here the dipole moment is in upward direction, and on the equatorial line the field will be in downward direction. So here the field is like this. So the E1. So its magnitude we can write as kp1 by r cube. So it's the direction of that is the magnitude of electric field, and the electric field will be in downward direction. Now I am writing the potential energy of this dipole. So potential energy is equal to minus P2 into E1 into angle between them is 180 degrees. So Pt is upwards, E1 is downwards, and therefore this is equal to K into P1 P2 by R power 4. That means now here it is cos 180 minus 1, so minus of minus plus you get. So again we know the force and potential in the relation. So F is equal to minus du by dr. So F is equal to minus K P1 P2 into d by dr of 1 by, so this is r cube. So r cube we need to write. So therefore there again minus 3 you will get. So it will be plus you will become, because here this minus is there here already. So pk p1 p2 by r power 4 unit. So this is a that means force between the two dipoles when the dipoles are placed in parallel to each other. That means now here the force is positive force we are getting here finally. Positive force in the sense it will be repulsive in nature. So simply you can observe that the dipoles are, how to explain this is repulsive force in the sense you can consider this. Now this is the dipole direction, so like this is the negative charge and this is the positive charge here for the first dipole. And similarly here for the second dipole, if you consider this is a negative charge, positive charge and this is a negative charge here because both are in the same direction like this. And so now here these two positive charges are closer to each other and similarly these two negative charges are closer to each other. And so automatically there is a repulsive force between them. So that the force between them is repulsive. If we reverse the one of the dipole here, then automatically force between them will be attractive. That means if we reverse this P2 value, you can observe in this derivation, then here cos 0 you will get. Cos 0 means here negative sign will be there. Here minus of minus plus you will get. And in the integral, in the differentiation, you will get the negative sign. So finally, negative sign in the sense it is an attractive force you can conclude there. So that means that depends on the orientation. In the general case, if both are in the same direction, then you can conclude that the force between them will be a repulsive force like this. So that is a force between two dipoles there. And whereas if the dipoles are, for example, generally that case they won't give. For example, I am giving here the dipoles are placed like this. So one dipole is here, another dipole is like this. Then you can't calculate by using our this previous potential energy method, because if you write the potential energy of this configuration, here the electric field produced by this will be along this direction here, E1. Now E1 and P are both are perpendicular to each other, and our potential energy will become 0. P cos theta minus P cos theta we are writing, so potential energy is 0. So that method is not applicable here. Then actually in that case what we will do is, if suppose here there will be the positive and negative charge distribution here, then we calculate the field due to this dipole at this point, and that force will be along this direction, say E1 into Q. And the field due to this dipole at this point, this field will be along this downward direction here. The field due to the dipole of the equatorial line, say at a distance of r1 from this. So that will be in downward direction. We can field will be in downward direction. I can write E1. So force acting on the dipole will be opposite. Force acting on the negative charge will be opposite to that. And so that will be like E1 into Q. We can write. And at this point, this distance will be E2. So then its magnitude will be E2. You will get. Sorry, this distance is R2. And so then here this field is E2. And that force will be in the same direction. You will get here. That force you can write as E2 into Q. You can write. This is say F1 and this is F2. So then F2 minus F1 minus F2 we need to find here, because these two are unequal. Because the distance of positive charge and negative charge is different. So then we need to write like this, where E1 is given by Kp1 by R1 cube, and E2 is given by Kp by R2 cube, P1 by R2 cube. And therefore our net force is nothing but E1 minus E2 into Q. We need to write here, just by substituting those. Generally they won't give the case. If they give such a case, then we need to calculate like this. So for this case, our potential energy method is not applicable, because the potential energy of the dipole is 0 for the case here. So those are some problems based on this dipole. And I will give one more problem based on the dipole and dipole moment calculation, field calculation. Solve it. It's not the force or interaction problem. So linear charge density on a circular non-conducting ring is varying like this. Suppose I am taking this as like y and z axis, and this theta is defined here. This is the origin. That means the linear charge density on a ring is varying like this. Lambda is equal to lambda naught into cos theta, where theta is defined as shown in this. This is a circular ring of radius r. whose center coincides with the origin. Now our questions are: find dipole moment P, and the second question is find electric field at the center. Actually, these two calculations we already calculated. We already did in the previous process. Now, additional I am calculating. Find E at like x comma 0 comma 0. That means on this x-axis. On this x-axis or on the axis of the ring, we need to find. So these two problems we already did. So we can easily write those expressions there. Now additionally, you need to calculate this one. The electric field due to this at this point. So try that problem. Otherwise, I will explain in the next class. That means electric field on the axis of the ring we need to calculate. So that is that problem there. So now those are some problems based on the dipole. So with this, we finished with this dipole concept. Field, potential, and time period, and how the force acts on the dipole when it is placed in uniform or non-uniform electric field. So all the concepts related to those dipole concepts. And so in the next class we will start our Gauss law and electric flux and the Gauss law and applications of the Gauss law. So for this week you have to solve up to here. That means for this week our syllabus will be from potential due to point charges, continuous charge distribution, and potential energy concepts, and this electric dipole concept. That means last week and this dipole here, up to dipole concepts here, this week's syllabus. So solve all the problems based on the dipole. Complete all the problems based on the dipole, and if any remaining problems are there based on the potential, and complete those problems, cover those two topics for this weekend examination. Thank you.